Welcome to AP Chemistry at Hononegah High School. Today's movie we will deal with differential rate law practice because one of the most important ways to help prepare yourself for material from kinetics is to practice it enough times till it becomes second nature. And differential rate law is the only type of data table that you'll see that includes concentration and rate data. So once you see concentration and rate data, that tells you right away it's going to be a differential rate law. And one of the things that you need to understand is if it's a differential rate law problem, you're always going to be finding two things. First, what is the rate law expression? And second, what is the value of K, the specific rate constant or rate constant? So when you go to do those two things, you need to understand all rate law expressions fundamentally look the same. It's going to be rate is going to equal K, our rate constant, times the concentration of the one substance raised to some power times the concentration of the other substance raised to some power. So we have two reactants here. What we really need to find out is how, if at all, those concentrations are relating to changes in rates. And those question marks are in the exponent spot because that's how these things are related. If it's zero order, that means something to the zero power. That means it's going to reduce to 1, which means it has no effect on the overall rate. So if it ends up zero order, our coefficient would be 0, and that means it's not dependent upon the rate, or the rate is not dependent upon that concentration. If it's first order, that means that when you double the concentration, you would double the rate. If you triple the concentration, you'd triple the rate. So 2 to the first power equals 2, 3 to the first power equals 3. And if it's a second order situation, that means when you double, it's going to quadruple the effect. When you triple, it would be 9 times bigger because it's a squared effect. So really what we're trying to find out is it 0, 1, or 2? What is the power that deals with the relationship between concentration changes and rate changes? Now, when you go to do that, you first need to establish, you pick which one you're going to look for. In this case, let's look for A first. So what's going on with the concentration of A as it affects rate? Well, if we're looking closely at the concentration of A to determine its order, we need to pick a situation, or it's a lot easier to pick a situation where B is staying constant. Because if B is constant, it's not affecting the overall rate, and therefore all rate changes are caused by changing the concentration of the other substance. So when I look at the data here, I see 0.48 is the first one. Well, there's nothing below that's 0.48. But Experiment 2 and Experiment 4 are both 0.120. So I have a situation in Experiment 2 and Experiment 4 where my concentration of B is staying constant. And that means all of the change that you see observed in the overall rate are going to be caused by substance A. Now, ideally, when I'm going to pick two situations where B is constant and where A doubles, because a double relationship is much easier to handle in your head. But really, any sort of change can be predicted mathematically. So we're really looking at here Experiment 2 and Experiment 4. Now, if you notice, in Experiment 4, the concentration was 0.120. In Experiment 2, it was double that, 0.240. So really, the change in these concentrations is a doubling situation. It's a times 2 in terms of the A. And remember, order is to what power we have to raise that ratio of concentrations to equal the ratio of the rates. Well, between Experiment 2 and Experiment 4, the rates were 2.00 and 0.50. So if you take and divide 2.00 by 0.5, you get 4. So when I doubled A, that resulted in a change of 4 for my overall rate. So what order, what exponent would give us that 2 becomes 4? Only when x equals 2. So with respect to A, the order of this reaction would be second order because doubling A quadrupled the overall rate. Now, when you go to find out what's going on with B for its order, you essentially do the same thing. You want to identify a situation where A is constant. Well, if you look at Experiment 1 and Experiment 2, A is constant. So I could use these two rate ratios to calculate my overall, or my order with respect to B. The thing is, I always try and look for a simple situation. And a simpler situation would be a situation where A was constant but B doubled. And if you look at Experiment 2 and 5, A is still constant, and in these two experiments, I have 0.12 and 0.06. That's a doubling situation. So I'm going to look at experiment 2 and 5 to figure out what the order is of B, simply because it's going to be a little bit easier. So I noticed that that's going to double. So my relationship here is I've doubled it. So what's happening between those two experiments and my rate? Well, when I doubled the concentration, I doubled the rate. It went from 1.00 to 2.0. So 2 to what power equals 2? Well, in this particular case, that would be first order, x equals 1. So I know it's second order with respect to A, and it's first order with respect to B. And remember, it's optional whether you write that 1. If you don't write the 1, it's assumed that it's 1. So the rate law expression for this equation would be rate equals K times the concentration of A squared times the concentration of B. Now, the second question in a rate law problem, a differential rate law problem, is always to calculate the value of K. And if we look up here to the equation that I just boxed, that's basically where my K is. So K is going to equal, if I solve this algebraically, the rate over the concentration of A squared times the concentration of B. So all I really have to do is plug in values for those, and I can determine what my K is. Well, if you take a look at your data table, I've got lots of data for concentrations of A and B and for rates. And honestly, all of them should return the same information. But notice 6 doesn't have anything for the initial rate, so that's an unknown. So basically, I can use any information from experiment 1 through 5 to plug into this equation to calculate my K. Typically, you only have to do it one time. The only time I'd recommend you put in multiple Ks is if you're doing something truly in the lab, so it's experimental, or if it says what is the average value of K. So in this particular case, I'm just going to use experiment 1. The rate for experiment 1 was 8.00, and the units for that, it says moles, liters to the -1, hours to the -1. Remember, those -1s mean they're on the bottom. So it would be moles over liters, well, that's just molarity, over hours. So that would be my unit for that rate. Now, it would be the concentration of A squared. Well, A is 0.240, so 0.240, and my unit there would be molarity squared, times the concentration of B, which is 0.480 molar. So you plug these into the calculator and round to the correct number of significant digits. In this case, everything's got 3, so I'd round to 3, and you would get 289. And my units would be, if you double check, well, these molarities are going to cancel. So I'm left with hours on the bottom and a molarity squared on the bottom. So my unit is going to look like this. 1 over molarity squared hours, which could be written as molarity to the -2, hours to the -1, same exact thing. So now I've solved for my rate law expression, and I've solved for my value of K. Part C here says calculate the value of the initial rate of this reaction at 30 degrees Celsius for the initial concentration shown in experiment 6. So what they're asking us to do is define that if these are my two concentrations. Well, all you really have to do is, once again, go back to your rate law expression. It's asking me to calculate rate, so I'm trying to find rate. Well, remember, rate equals K, which we just determined was 289, times the concentration of A. Well, in experiment 6, A is 0.0140, and that's molarity, and that's going to be squared, because it's second order with respect to A, times the concentration of B, which is 1.35 molar. So multiply that out in your calculator and round to 3 significant digits, and you have an overall rate here for this situation. An initial rate for experiment 6 would be 7.66 times 10 to the -2. And when you multiply out and cancel, those cancel. I'm going to be left with molarity on top and hours on bottom, which makes sense. I'm calculating a rate. It should be change in concentration over a change in time. So that's how you would do problem number 1. Problem number 2, similar type situation. We're given concentration and initial rate information. Now notice the table is written a little bit differently. The initial rate's written at the beginning, but I'm still given concentration rate information. It's still going to be a differential rate law, which means the first thing they're going to ask me is, what is the rate law expression? So that's right there. So go back to the same idea as you did last time. If we want to find out what order it is with respect to x, because remember, it's going to be the rate equals k times x to some power, oops, question mark, times y to some power. And our job is to find out those two question marks. If I want to find out x, I want to look for a situation where y is constant. Well, if you take a look, y is never constant. Well, that's going to complicate the situation here just a little bit. But what it really means at the beginning is I'm not going to look for the order of x first. I'm going to look for the order of y, because I do have two situations here and here where x is constant. And you'll notice it's a nice situation here. I always look for the double situation. And sure enough, between these two, I've doubled the concentration. And if you look over here, between those two, that means I doubled the rate. Well, if you double the concentration and it doubles the rate, that's a first order relationship. So I know with respect to y, it's a first order reaction, because remember, x was constant, so it didn't have an effect on that rate. So I know it's first order with respect to y. So how do I go about tackling that problem of how do I determine x if y is never constant? Well, what you really need to understand is, now that we know y is first order, we can account for its changes in the overall rate and see how x affects it. So we're going to use a situation here, and honestly, I can really pick any. So I kind of like 1 and 2, because I noticed that that's a double situation and that's a double situation, and I like doubles because it's easier to see what's happening with the math. Now, one problem here, you'll notice that my exponents, so here my exponents, they're not the same. It makes it a lot easier to intellectually, and more importantly, just off the top of your head, see exactly what's happening with these if the exponents are constant and consistent. So if this is 10 to the negative third, that's going to mean 0.7. So 0.7 times 10 to the negative third is the same as 7.0 times 10 to the negative fourth. Now it's going to be a little bit easier for me to see how my rate changes are occurring. So remember, we know y is first order. So we know if we double y, that's going to double the rate. Well, if I double that rate, I'm going to get 1.4 times 10 to the negative third. So when I've accounted for what y is doing, that means my rate should end up 1.4 times 10 to the negative third. And now what you do is look at what x does in addition. So now I've accounted for what y does. Now I want to compare these two. So think of it as this is my new rate situation, and I want to compare that to the final rate. And what I end up with here, well, it's 1.4 times 10 to the negative 3, 1.4 times 10 to the negative 3. When I double x, I do absolutely nothing to the rate. All of my change in rate was accounted for by my change in y. So that means, and this is rare, but it does happen, in particular in the AP test, that we are zero order with respect to x. Doubling the concentration of x made no effect on the overall reaction rate. So that would be my rate expression. Now keep in mind, that's the exact same thing as this. You don't really have to write that x to the 0. So the rate in this particular case is going to equal k times the concentration of y, because it was first order with respect to y. Now to calculate my specific rate constant, remember that's k. So rate equals k times the concentration of y. So k would equal the rate over the concentration of y. And once again, all of my data should be valid for this, so I should be able to take any situation here from my data table to determine my value of k. So I'm just going to take the very first one. The rate in the first one was 7.0 times 10 to the negative fourth. And that would be in units of molarity, or moles over liters and seconds. So that would be molarity per second. And I'm going to divide that by my concentration of y. Well, the concentration of y was 0.10. Remember, x doesn't make any difference, so I don't plug it in. Well, 7.0 times 10 to the negative fourth divided by 0.1. This one's easy enough. I can do that one on my head. Ends up giving you a value of 7.0 times 10 to the negative 3. And that would be molarity on bottom, molarity over seconds on top. Molarities cancel. I've got inverse seconds for my K value. Now remember, one of the things we talked about in class and in earlier notes is once you know what the overall order is, you're always pretty much going to know what the overall units are for the value of the rate constant, because it's always going to be basically 1 over some time unit. The time unit in this case was seconds, and you might have an m. So basically take the overall order and subtract 1, and that's how many molarities I'm going to have on the bottom. Well, the overall order here is 1. 1 minus 1 is 0, so I'm not going to have any molarity on the bottom. If it was second order, that would be 2 minus 1, so it would be 1 over molarity second. Okay, that brings us to FRQ number 3. Once again, I'm given concentration and rate data that pretty much clues me in on the fact that this is going to be a differential rate law type problem. Now, first thing I always do then is calculate what the rate law is. Same thing as always. I want a situation where one is constant and the other, if I get my wish, doubles. So if I look right here to figure out what's happening with this one in the rate law expression, because remember, it's always going to be the rate of one to some power times the rate of the other to some power. C2042 minus is constant in experiments 2 and 3, and this is doubling. So when that doubled, what happened to that? Well, it's pretty close to doubling as well. So doubling leads to doubling. That would be a first order relationship. So it's first order with respect to HgCl2. And that then leaves C2O4. So let's look at a situation here where H2Cl2 is constant and C2OCl4 hopefully doubles. Well, that's 1 and 2. In 1 and 2, these two are doubling. And if you look, 2.08 divided by 0.524, that's a quadrupling situation. So when my concentration doubled, my rate quadrupled, that would make it second order with respect to C2O4. And once I know that, that gives me my blanket equation to solve for K. K would equal the rate of the concentration of HgCl2 times the concentration of C2O4 2 minus squared. And remember, I can pull any of my data from up above to do that, so I'm just going to go with experiment 1. Experiment 1 was 0.52 times 10 to the negative fourth. My units, molarity per minute. And that's going to be over HgCl2, which is 0.0836. And that would be molarity, because it's got brackets. And then that's going to be multiplied times 0.202 molarity squared. And when I plug those into my calculator, my K value is going to end up 1.52 times 10 to the negative second. And my units would be, now remember we just talked about this a second ago. Take the overall order and subtract 1. That tells you how many molarities you got on the bottom. Third order, I should end up with 2. And my time unit here was minutes, I believe. So 1 over molarity squared minute would be my unit. Next, what is the numerical value for their initial rate of disappearance of C2O4 for experiment 1? Well, if you take a look at the top equation, it says the equation for the reaction between these two substances in a hot aqueous solution is shown above. The reaction may be determined by measuring the initial rate, and it's the initial rate of the appearance of Cl minus. Now notice it's asking me about the disappearance of this substance. Now my problem is, if I use this rate law expression, my data pretty much locks me into the fact that I'm going to be using it for Cl minus. So what I need to recognize here is this asked about something that was not Cl minus, C2O4 2 minus, and how it disappeared. So I'm going to use my rate equation, but remember that's going to give me data with respect to Cl minus. Now since I used a first order, second order situation here, if I plug in experiment 1, because that's what it asks about experiment 1, I'm going to calculate a rate. In this particular case, that's going to equal rate is the rate constant, which was 1.52 times 10 to the negative second, 1 over molarity squared minutes. That's going to be times the concentration of HgCl2. That would be 0.0836 molarity times the concentration of my other substance, which is 0.202 molar. And that's a second order relationship, so it's squared. When I actually do this calculation, I'm not going to get my final answer, because in this particular case, I'm calculating this with respect to Cl minus. So this rate is for the rate of Cl minus, and it ends up being 5.2 times 10 to the negative fourth, and that would be molarity per minute, since I'm dealing with a rate. But that is with respect to Cl minus. So to find out what that would be for C2O4 minus, I have to go up and look at the stoichiometry of the problem. Whenever you're going from one rate to another rate, you're doing relative rate stuff, that's where stoichiometry comes into play. You'll notice that that it's a 2-to-1 ratio. The Cl minus is appearing twice as fast as the C2O4 2 minus is disappearing. So to get our final answer here, I really have to multiply this by 1/2, because the the rate of Cl minus is going to be double that of the rate of C2O4 minus. So really, I take and divide this by divide by 2 or multiply by 0.5, and my final answer would be the rate is 2.6 times 10 to the negative fifth molarity per minute. And that would be with respect to, so this is the rate of C2O4 2 minus. So it's a rate with respect to that substance. Now the last one here, calculate the initial oxalate ion concentration for experiment 4. When I go to do this, notice it's asking about oxalate. So I basically have the same exact issue. Okay, let's calculate the initial oxalate ion concentration in experiment 4. Oh, experiment 4 was missing a number. So they're saying in experiment 4, what really should that be? Now remember, experiment 4, like all the rest of them, follows my general rate law expression that I established back here. So if I want to find that particular concentration, what I really need to do is solve my equation for my unknown, which would be right here. So that is going to be x. So when I set this up, I know the rate in experiment 4 is 1.27 times 10 to the negative fourth. So I know that information. And if I divide that by K and my HgCl2, which, remember, the K value was 1.52 times 10 to the negative second. And I also have to divide that by my initial concentration of HgCl2, which is 0.0836. That will give me x squared. So if I really want to solve for x, I need to take the square root of that value. So to calculate the initial oxalate concentration in experiment 4, the number right here, it would be the square root of what I've got. And the final answer here, I'm running out of room, so I'll just write it up top here, is going to equal 0.514 molar. So when you solve that equation to 3 sig figs, you get 0.514 molar. So that would be problem number 3, which finally leaves us with problem number 4. Remember, if you know what you're doing and everything makes sense, you may not be here at this point. So keep going until you're comfortable. Okay, I've got concentration and initial rate data. That means I'm going to be doing rate law expression. Sure enough, right there, what's the rate law expression? To find out what the rate is with respect to ClO2, I need a situation where F2 is constant. That doesn't happen. So that pretty much means I'm stuck with finding F2 first. So I'm going to switch gears, and I'm going to look for a situation where this one is constant. Sure enough, right there, that is constant. This is a quadruple situation. 0.1 to 0.4 is quadrupling. What ended up happening to my rate? Well, that also quadrupled, which tell me we are first order with respect to F2. So in my rate law expression here, I know I'm going to have the rate is going to equal K times the concentration of ClO2 to some power times the concentration of F2, and I just determined that was first order, so the first. Now, I have to go through and basically do the same thing I did previously. I now know what F2 is, so I know what F2 is going to do to my overall expression. So I'm going to look at experiment 2 and 3 here. Now, that's a nice simple double situation. So I know between these two, that's going to cause a doubling. Now, when you take a look at that, well, this didn't change. Well, how can that happen? Well, if you take a look at what's happening here to here, it's not doubling, it's 1/2. So if I double this, and then it's first order with respect to the other one and cut it in half, I should get no change. So that pretty much tells me when I look at that it's also going to be first order with respect to ClO2. Now, if you're having trouble seeing that, you can always change tacks here and look in a slightly different situation. Now, I just looked at what was happening with experiment 1 and 3, or 2 and 3. Let's look at what's happening with 1 and 3, and maybe it'll be a little bit easier for you to follow the relationship. So in 1 and 3, what does F2 do? Well, it doubles. So that means I should double the rate because it's first order with respect to that. Well, that would give me 4.8 times 10 to the negative third. So think of it as that is my new rate. Now, what happened here is also a double. Well, I doubled this, and 4.8 to 9.6, that's a double that. Double, double, that would be first order. So remember, if you're confused by the first way, looking at experiment 1 and 3, it was much easier to see that it was first order. Then to calculate the value of K, just like we've always been doing here, K would equal the rate. Well, I'm going to pick experiment 1. So 2.4 times 10 to the negative third, and that would be molarity per second. And that's going to be divided by the concentration of the first substance, which is 0.010 molar. Since it's first order, it's just times the concentration of the second substance, which, oops, no, I did write that right. So 0.1 molar. And when I calculate, I end up with 2.4. And if you take a look here, molarities cancel. I'm left with 1 over molarity second, which makes sense because overall it's second order, so I should have 1m there on the bottom. And that ends our look at